looking a little bit thin in here today. So. It's not too bad though when I count. Okay. Here's our reminder on what we've got coming up on WebAssign. Okay. 2.2 due tonight. If you haven't got that finished yet, and then 2.3 Friday, and 2.5 will be next Wednesday. Have a little bit of a break if you get that one done. Take a little bit of a break. Because we didn't finish the section, right? So we kind of got a night off on those. So just one thing I want to mention here, because I don't remember, since I've got it fixed anyway, since that first assignment, I don't remember anybody using it. But if you get stuck on a question, got that Ask Teacher button on there. A couple of you had asked questions on the very first assignment, and I didn't have it set up where it came to my email, so it took a while before I noticed. If you get stuck, if you hit that button and type in your question, it lets me see the problem you're working on, so that helps me know how to help, and then it'll send me an email, and I'll get back to you as soon as I can on it. Usually pretty quick when it comes to my email. So. I am getting old, so I do go to bed pretty early, but if you're working on it early in the day or something, I'm pretty quick. Okay. Anybody struggling on having trouble with any of the problems I need to talk about? Nothing too bad so far? Okay. Just know that you are welcome to bring homework questions to class. One reason why I give you such a, I'll give you a week typically before something's due. Okay, so we are maybe 2/3 of the way through the continuity section. And so we'll finish up continuity, and then we'll start on the next section. Okay, we won't get finished with it today. I don't even have the assignment finished yet to put out there, so I don't have to worry about it yet. How's everybody's semester going? All right. We're having a rough semester. A couple of you have. Sometimes the semester you start the calculus sequence is a rough semester for some majors. So if you're on, if you're on the normal schedule, not everybody is. But. Okay, so let's see what we can remember about continuity from last time. If we're thinking about drawing a function, what was it we said just, informally? If we could draw a function draw a graph of a function without what, then we say it's continuous. Yeah, we can draw it without picking up our pencil or pen, whatever we're using. Yeah, then we say it's continuous. So that's kind of our informal idea. And then we got a more formal definition. We said that a function is continuous at a number a if the limit of the function as x approaches a is the same thing we get when we find f of a, when we plug it into the function. So if the limit is the same thing as the functional value, then the function is continuous. But we said that really had more going on than appears on the surface, right? We had to have three things. In order for that to be true, we had to know that the function was defined at that number. Because if it's undefined, then it's not going to be continuous there. The limit has to exist at that number. And then if we have both of those, then the limit and the function value have to be the same. Those are our three things. And then we looked at the picture and gave names to a couple of different ways we can have that breakdown. a couple of different ways we can have discontinuities. So we said if we have a hole, have some x value for our functions not defined, and we have discontinuity there. And not only that, we said we would call that a removable discontinuity, because all we have to do is redefine our function at that one point, and we can fix it. That's removable. If we have a situation where our function's going off to infinity or negative infinity, then our function value is not going to match our limit there, so we'll call that an infinite discontinuity. And we had a third type. You remember what it was? Had a removable or a whole infinite discontinuity. What was the other one? Another way I could break it down. Have a jump, right? We'd have a jump. We have anywhere where our y values change suddenly, we have a jump. So we could say we have a jump discontinuity. And that one has a bunch of jump discontinuity. We said that greatest integer function has a jump discontinuity at every integer. That one had infinite amount of discontinuity. And then we just talked, we gave the names. That was the last thing we did there. Okay. So the next idea we need to talk about a little bit. You could say this idea of continuity we've been talking about, kind of like we did with limits. You could call this idea of continuity two-sided continuity, because we can just think about it just coming from one direction. Then we can think about a function either being continuous from the right or continuous from the left. It's an easy adjustment. We need the same properties we had with others. But when it comes to the limit part, the only thing we care about is that the limit from one direction, either the right or the left, matches our function. So here we can say a function is continuous from the right if as our limit as x approaches a from the right. It's the same thing we get when we plug into the function. And then there we got from the left. So if we think about that, then we can talk about one-sided continuity. One-sided continuity there. When that's really helpful, and we'll see some graphs, or a graph anyway in a minute. When that's really helpful is if we're thinking about this last thing. This definition down here says we can say a function is continuous on an interval if it's continuous at every number in the interval. Okay. So maybe we could say a function is continuous on the interval 0 to 1. And that means every number in the interval 0 to 1 meet all three of our properties. But then the part that gets a little tricky about that, when you're talking about an interval, are the endpoints. Because if you're just thinking about a function starting at some number and ending at some number, then usually we don't have a two-sided limit at those, because we're kind of cutting it off at the endpoints. So what's implied there, if we say a function is continuous on an interval, we mean every number inside the interval is continuous, and that the left endpoint is continuous from the right, at the right endpoint continuous from the left. All we care about the endpoints make things a little trickier. Good idea there. Okay. So with all that, okay, here's the payoff part. We got the maybe boring part out of the way. Here now we get the payoff, how we can make good use of this continuity property. Because it is really nice and it gives us a lot of benefits if we know that the function we're dealing with is continuous. So here's first big payoff. We have two continuous functions, f and g, where they're continuous at some number a. And then we got a constant c. And then we get all of these things. We know that f plus g is going to be continuous at a. We know that f minus g is going to be continuous at a. We know that a constant times one of the functions f or g, is going to be continuous at A. We know if we multiply the two functions together, our product is going to be continuous at A. And then we know if we divide the two functions, it's going to be continuous at A as long as, division always gives us a little extra trouble, as long as when we evaluate the denominator at A, we don't get 0. And then we'll have a continuous. So one reason that's so nice is if we have a situation where we've got like f plus g, two functions added together, we don't have to go all the way back and check all three of those properties if we already know that f and g are continuous. Okay? We're guaranteed that f plus g will be continuous. And kind of have to take it back if you're following where we're headed with this. Okay? We said earlier in a different section that if we have a continuous function, we can find the limit using direct substitution. Right? That's the easiest way to find a limit is direct substitution. And we can do that with all continuous functions. So now all of a sudden we can use direct substitution on a bunch of different kinds of functions and know that it's correct. As long as the parts of our function are made up with addition, subtraction, constant multiplication, multiplication between two functions, or division between two functions, given this, then we know the function we end up with is going to be continuous, so we can just use direct substitution. Okay. That saves us a lot of headache. So let's look. Here's our theorem that says that. So we already have talked about that any polynomial we have is going to be continuous everywhere. We know that because direct substitution works with polynomials. So by definition, they're continuous. Okay, so for any value on the real line, okay, negative infinity to positive infinity, polynomial is going to be continuous there. Continuous everywhere. If we think about rational functions where we've got a fraction of two polynomials, right? Polynomial on the top, polynomial on the bottom, they're going to be continuous everywhere as long as the function is defined. So as long as our denominator is not 0, the rational function is going to be continuous. And really, there are a lot of functions that turn out to be continuous. And we got polynomials and rationals so far. We're building our toolbox up. Okay. Think about some formulas like from out in the world. Okay. If we can think about volume. Sorry, getting ahead of myself. We can think about the volume. Here we've got volume of the sphere, so we could think about that as a function of the radius of the sphere. This would be our formula. And I know it's continuous. So this is just a polynomial. Right? 4/3 and pi are just constants. So I just have some variable raised to a power. That's a polynomial. So that volume function is a continuous function. And if you think about that kind of intuitively, that makes sense, right? The volume of a sphere is going to like increase gradually. We're not going to have like a jump discontinuity or anything. Okay. Here's another one. So a lot of the physical world, the functions that we use to describe the physical world are continuous. Okay. We got the height of a ball in feet after t seconds. So you could call it h of t if you wanted to. And our function there is just a polynomial in t. So that's a continuous function. We get all the nice properties that go along with that. Okay. So here's one more. This one's good for us. Well, so what are we on here? We're on the unit circle. Okay, tracing the unit circle. Okay, if we think about sine and cosine, here we're going to think about finding the limits. So as theta approaches 0, so we're going this way down our unit circle. Cosine, what's it going to approach? Cosine is like the first coordinate, the x coordinate. So we're approaching this point. So as theta approaches 0, cosine is approaching 1. And as sine of theta, here theta is approaching 0, so sine of theta is approaching 0. And because cosine of 0 is 1, sine of 0 is 0, both of these are continuous. Both of those are continuous. So there we got sine and cosine are continuous. And because their limits match their function values, they're continuous, their definition. And then we can extend that to think about tangent. Tangent sine over cosine. So that's division. We know the division of two continuous functions is continuous everywhere that the denominator is not 0. The tangent's going to be continuous everywhere except where cosine is 0. So where cosine is 0, and we actually have infinite discontinuities. We got all the multiples of pi over 2. But in between those, everywhere tangent is defined, tangent's continuous. So it's continuous everywhere that's in its domain. So not at the multiples of pi over 2. Cosine 0 there, tangent's undefined. But everywhere else, okay, tangent is continuous. So if, what all we got now? We've got sine, cosine, and tangent are continuous everywhere in their domains. So we could also flip them and take the inverse, trig functions. What's happening on the graph when you compare a function to its inverse? Do you remember that? So if you compare a function with its inverse, comparing the graphs, what happens is we're reflecting the graph around the line y equals x, because we're switching the x's and y's to inverses. So you can intuitively think about it that you have something that's continuous and then you reflect it around y equals x, it's still going to be continuous. So we get inverse trigonometric functions that way. So what we got? We got polynomials, rational functions, trigonometric functions, inverse trigonometric functions. Root functions or radical functions are also continuous everywhere in their domain. And then we're adding 2 more we haven't talked about much yet, but we're getting there. We've got exponential functions and logarithmic functions. Those are continuous everywhere in their domain. So a lot of the common functions we work with are continuous. And so all of a sudden that gives us option to find lots of limits using direct substitution. And we can even add, well, not quite yet. Let's look at this theorem now that we've got all these. Look at this theorem. It says if we've got a continuous function f and it's continuous at the number b, and the limit of another function g equals b, what's going on? It says the limit as x approaches a of f of g of x equals f of b. That's kind of hard to keep track of. Okay. Here's the English version of that. Okay. So if we've got a function inside of another function, we want the limit. If we know we have continuity and the values we're dealing with, you can move the function out in front. You can take the functional value of the limit inside function. So continuity lets us move the function from inside the limit outside the limit. And then one that's even more useful than that. We're going to do some examples. One's even more useful than that. It says if we have two continuous functions, and so we've got g is continuous at a, s continuous at g of a, it's just a number. And then the composite function is continuous. So f composed with g continuous. All right, so let's look at some examples, and then we'll come back and do this last theorem. Look at some examples. There's only so much just looking at theorems and stuff you can. Yeah, it's the life of a math major just looking at all that theorem junk. So you should feel sorry for us. So let's look at something like this. See, we might get an nasty number here, but so in limit notation, we're looking for the limit x approaches to 2 root x squared minus. So we've got all those properties we've just seen that we can use. Why can we use those? Let's look at each little piece of this. Let's start with the inside. If we just have the function x squared minus 7, what kind of function would you say that is? X squared minus 7 is it's quadratic, and quadratic is a special polynomial, not polynomial. So x squared minus 7 is a polynomial. So in light of what we've been talking about, what do we know about the x squared minus 7 part? It's got to be continuous. Got to be continuous. Okay? And then if you go back to our list, okay, so now we've got a continuous function in here. We want to take the square root. So we've got a root function or a radical function. So that's on our list. Radical functions have to be continuous. And then all that's times 2. Okay? So big deal there. We've kind of already seen with these, we can bring a constant out front. So we don't have anything to worry about. We've got all continuous functions here. Okay. Even though we've got a polynomial and composed with a radical and then times a constant. That's okay, right? You don't have to write all this down when you're doing these, but we can bring the 2 out. We've got a property that says we can do that. We could bring the radical out. We've got a property that says we can do that because of continuity. And that part, we're back to stuff we know how to deal with. It's just finding the limit of a polynomial. So really all we have to do on this one, how can we find the limit? This is the good news, right? These are not hard. We just use direct substitution. Direct substitution. So let's see. 2 squared is 4, minus 7 is -3, so I gave us an ugly one, but that's what happens when the teacher makes up problems off the cuff. There would be our limit if that was real. Since that one comes out as a complex number, we would not be dealing with that in here. You just use direct substitution. Not bad. So let's look at another one. I'll try to get us one that comes out with a real solution. How about this one? It's similar, but a little bit different. So we don't have a constant out in front, so that's not quite as simple. But look at the pieces of what we're working with. Again, inside, polynomial, so it's continuous. Square root means it's going to still be continuous. Multiplication, so this is just another polynomial. So if we multiply two continuous functions together, we know it's got to be continuous. Everything in here tells us that this thing is continuous, so finding the limit's not bad. Use direct substitution. Oh, maybe this one comes out better. That's square root of 8 minus 4. 4, that one's nicer. So, fairly complicated function, but because of all that continuity, not bad. Just turns into arithmetic, finding the limit. The only reason why I said easy is because of that continuity. Okay. Let's see. Look at another one. Another one I'm making up, so it might go bad. Let's see. That could potentially be kind of nasty to find the limit. We don't have a 0 in the denominator here, and if we try to do direct substitution, so that part's okay. But are we safe to do direct substitution? Yeah, we are. And the part under the radical is a polynomial. They're continuous everywhere. Then we've got a square root, so we'll still have continuous function there. And then we're dividing by x minus 2, which is still going to be continuous. So not at x value of 2. So then we just use direct substitution. Square root of 9 is 3. -1, so 3. Easy calculation. But it's an easy calculation built on the back of for a good bit of theory. Got all that continuity working. Okay. Not bad, not bad. So one more little theorem, we'll be done with this section. I say little theorem, it's an important theorem. it maybe doesn't feel all that amazing when you see what it's saying, but it can be very useful. Very useful. So it starts off at the bottom there. So it says take a continuous function, continuous on the interval a to b, and we're going to pick n to be some number between what we get when we evaluate our function at the endpoint. So n some number between f of a and f of b. And these two can't be the same. And so we're taking the possibility out that we have the same functional value at both endpoints. So then with those conditions, we're guaranteed, and we've got an existence theorem here, okay, is we're guaranteed that there's some number in our interval a to b, not at the endpoints, so that when we plug that number c into our function, we get n. And n is any number between f of a and f of b. So we really are getting a lot of values that we're guaranteed are in there. So if we can pick an n that's between the f of a and f of b, there's some number in our interval that when we evaluate our function at that number, we're going to get. If that's a little hard to wrap your head around, here's the picture. We're saying, so we've got some function, some continuous function on this interval a to b. So blue lines are continuous function in that interval. Okay, f of a would be our y value down here. F of b would be our y value up here. So we're saying if we pick any number n as between f of a and f of b, then there's got to be some number down here on the x-axis so that when we plug that value into our function, we get n. So think about it the other way around. Think about what it would be saying if that didn't happen. We would be saying that there's some way we have a continuous function, and if we pick a number between the function values, our y value range, okay, that there's some way it can skip over some values. But we can't skip over any values because our function's continuous. So a way to make that fail would be like if we could, so we don't want to go through the pink point here, like if we're trying to make this fail. So we would have to skip from like a y value here to a y value up here. You could, if we had a jump discontinuity, we could do that. Or if we had a hole right here, we could do that. But since we know our function is continuous, it's got to take on that value. Take on that value. It's the intermediate value theorem. Okay? It says that any number between endpoints, we got to have some number in the domain that gives us that value out of the range. No, it's not real exciting on the surface, but it turns out to be really useful. Okay? That's it. Intermediate value. And that's really one of the ways when you see software graphing functions. If we've got a curve in the plane, it really has an infinite number of points. So we would be waiting a long time if we waited on our computer to plot out an infinite number of points. Waiting an infinite amount of time. That's not what it does. Instead, it takes a large number usually, but a finite number of points and evaluates the function, and then it connects the dots. And that's okay if we have a continuous function, because the intermediate value theorem says there's got to be some x value that gives us those y values. Can't skip around anywhere if we have continuous. One way this. Okay, done with 2.5. Done with 2.5. You glad to be out of there? 2.5 is a little bumpy. Had a little more theory thrown in there than some of the other sections. Okay. So work on 2.6. So we actually are kind of focusing on a little bit more calculations section. So maybe it's a little bit more what you're used to in this section. All right, so two big topics, really three, but we're going to talk about limits at infinity. So what happens as our x values get really big? What happens as our x values get really small, like toward negative infinity? And along with that, we're going to talk about horizontal asymptotes. So we've talked about vertical asymptotes. We're going to talk about horizontal asymptotes and how to find those. Okay, so look at the function. We've got a rational function here. X squared minus 1 over x squared plus 1. And we want to think about what happens as our x values get really big. X values get really big. So if we have a really big x value, we're going to have some really big number squared minus 1 on the top, and then some really big number squared plus 1 on the bottom. We can investigate with a table of values if we want to. Here's a table of values. And look, as our x values get really large or really large negative, if you want to think about it that way. Here comes our pattern, and what's it look like we're approaching? Looks like we're getting close to 1, okay? We can reason our way through that without the table of values. We get a little practice thinking like this. Okay, so we have some huge number minus 1 divided by some huge number plus 1. Are the minus 1 and the plus 1 going to make much of a difference when we have really big x values? No, so basically what's going to happen when x gets really big, if x is 10 billion or something really large, then we're going to have some really large number over another really large number itself, basically. It's only different on top and bottom by 1. So if we have some number divided by itself, we get 1. So these are going to be really close to being some number divided by itself, so we're going to approach 1. So we can see that with the table of values. Okay, we're getting close to 1, both directions, when we go to the right or when we go to the left. And if we look at the graph, the blue line's the graph of x squared minus 1 over x squared plus 1. And then the number we're approaching, y equals 1. We would call that a horizontal asymptote. So our notation we use for saying that, if we're trying to talk about our x values getting really large, we would call this the limit as x approaches infinity. And so in this case, we could say the limit of this function as x approaches infinity is 1, what we've determined. And we can think about the same thing going the other direction as well. So here's our intuitive definition, and it says that this notation saying that we can make f of x get as close to L as we want to by picking x values that are big enough. And we can just keep making x bigger and bigger and bigger until f of x is as close to L as we would like. So with horizontal asymptotes, there's a few ways they can look. So our function may be approaching our asymptote from the bottom. Okay, you can do that. Our function may be approaching our asymptote from the top. okay? And then this last one might look a little strange to you if you're thinking about an asymptote. There, our graph actually crosses the asymptote over and over and over. If you look at that, it's actually going to cross our asymptote an infinite number of times as we move out to the right of our graph. That is a horizontal asymptote because our limit, as our x values get really big, will be that pink line, L. So basically 3 ways the horizontal asymptote can behave, or a graph can behave around a horizontal asymptote. Think about this with me, because all of the vertical asymptotes we normally talk about, they usually look like this, right? Like we'll have a graph come in and we'll say, oh, here's a vertical asymptote. So we say the graph gets closer and closer and closer to it, but it never crosses it. That's almost true. Almost true. There is another way they can look. So before we get to that kind of tricky fringe situation, why can a function not cross its asymptote? Why can we not have one that looks wavy with a vertical asymptote? So let me ask this. Let me give you a sketch. Why would have a wavy line coming in? Why would the y-axis not be the vertical asymptote of a function in that case? Yeah, so with horizontal, we're okay. It can do that. It can bounce back and forth across the asymptote. With vertical asymptotes, if we have that situation where we have that behavior where we're pinging back and forth, it's not a function anymore. Not a function because of our vertical line test. You can think about it that way. Like if we draw a vertical line in, it's going to touch our graph more than once, so that would not be a function. That's why we don't see those with vertical asymptotes, when we don't see it behaving that way, because then we're not talking about functions anymore. We're talking about different curves. But there is one situation that's kind of in between. Okay? So technically, if you hear somebody say that the graph of our function gets closer and closer to our asymptote, but it never touches it, never crosses it, really it never crosses exactly. It can touch it, and still be a function. Here's an example. So what about this? Let me draw it in. What if it just comes in and nicks it? It just touches. And that would still be a vertical asymptote. And because we only have one y value there. So we don't see it often. Okay? So like in 112 or something, we don't talk about it. But you can have a function that just touches in one place the vertical asymptote. It can still be a vertical asymptote. But we can't have the wavy situation like we do with the horizontal asymptote. Be aware of that. So let's go back to here. There's our. Okay, so same thing. This is just saying the same thing, but going towards the negative side. We won't spend much time there. There are two different graphs with horizontal asymptotes. So as we're going to the left, so as x approaches negative infinity, in both cases, the limit of f of x equals L. That's our definition. We did there. Let's think about the limits on these two. If you're in the back, you may not be able to see. The first one's approaching infinity, and the second one's approaching negative infinity. So we're thinking about in the first one, what happens when we have really, really large x values. So since it's 1 over x, if we have 1 divided by some really, really large number, and our number is getting bigger and bigger and bigger, we're dividing by. So if you divide by a bigger number, your answer gets smaller. And in the case when we're approaching positive infinity, our sign's going to be positive on the bottom. So we'll have a positive on the top, positive on the bottom, and we're coming in. And what's it look like our pattern is? We're getting close to 0. Close to 0. Okay. What about from the other side? So if we're going off on the negative side, let's think about that. So the only thing that changes is that the x values we're plugging in will be negative, but we're still getting larger and larger negative numbers. So like 1 over negative 100, 1 over negative 1,000, 1 over negative 10,000. So even though our answers are going to be negative, they're still trending toward, they're getting smaller and smaller in magnitude. So they're getting closer and closer to 0. And if you remember the graph of 1 over x, you might recall that. And here's our graph. Turns out to be a really important graph. You can get a lot of information from remembering this one. Okay. So horizontally, the x-axis is a horizontal asymptote. Okay. Or in other words, y equals 0, the x-axis. So 1 over x, if we're going toward infinity or negative infinity, it approaches 0. Don't get that confused with what happens around 0. Because around 0, the limit, the two-sided limit doesn't exist. If you approach 0 from the right, it goes toward infinity. If you approach 0 from the left, it goes toward negative. Okay? So you got to keep x's and y's organized in your brain. But as we approach infinity or negative infinity, our limit is 0. That turns out to be super useful. That would be super useful for us. Okay? And we can extend that idea a little bit even. Instead of just thinking about 1 over x, we can think about 1 over x to a rational power. And we need a positive rational power. Because if you get into negative exponents, it flips it. X to the r would be on the top. So it turns out, no matter, as long as our exponent is positive rational number in the bottom, that the limit going both directions toward infinity and negative infinity is 0. That's really nice. And that's going to lead us into how we can find other limits as we approach infinity. So let's look at this one. We got the limit of this rational function as we approach infinity. We want to know what that limit is. So if we just think about, you can't do direct substitution with infinity because it's not a number, but you can use the idea of infinity and kind of figure out what's going on sometimes. So if we think about, maybe we just think about substituting with a really large positive x value, then the terms that are going to dominate, okay, so here we've got an x squared term and an x squared term. When we start getting really big numbers, those are going to be so much bigger in the other terms that we really don't even, these really don't even matter anymore, kind of like the +1 and -1 did earlier. So really what's going to determine the behavior here is what happens with this 3x squared over 5x squared. And that's a little hard to determine because we've got some huge number squared times 3 over some huge number squared times 5. Like what wins exactly there? So the way we can analytically approach this is this last part. So what we're going to do anytime we want to find an infinite limit is we're going to divide every term in the numerator and denominator by the highest power of x that's in the denominator. That's what we're going to do. And we can do that. Sometimes you have to be careful dividing by a variable because it could be 0. Here we're not worried about that because we're not around 0. We're at the really far extreme right of our graph. So we're not even close to 0. So let's do that. We're going to divide every term by the highest power of x in our denominator. So what's our highest power of x in our denominator? Yeah, x squared. Okay, so that's what we're going to use to do our division. Let's do. The way the textbook goes through this one is a little bit confusing in my opinion, so we'll do it ourselves. Okay. We want the limit x approaches infinity. What was it? There's my goldfish short-term memory kicking in. It was 3x squared minus x minus 2 over 5x squared plus 4x plus 1. So we're going to divide every term by x squared. So it gets a little bit long, a little bit tedious. If we do that, let's watch what happens. Okay. So on the top, I'm going to have 3x squared over x squared minus x over x squared minus 2 over x squared over 5x squared over x squared plus 4x over x squared plus 1 over x squared. And then we'll cancel everything that we can cancel. So that top, the x squared's canceled, that leaves us with 3. X over x squared, what's that going to leave us? Yeah, 1 over 1 in the top when we cancel that x, and then 1x in the bottom. And then nothing cancels on the last one, so that's 2 over x squared. In the bottom, that leaves us with 5. Plus, we cancel out 1x, so we get 4 over x. And then the last one, nothing cancels, so 1 over x squared. Now, if you were writing down every little thing we were doing, the next thing you would write is we could split this thing up. Because we've got continuous functions. We're dealing with a polynomial over a polynomial. So we could say this limit is the same thing as the limit of 3 minus the limit of 1 over x minus the limit of 2 over x squared divided by the limit of 5 plus the limit of 4 over x plus the limit of 1 over x squared. That's a lot of writing down. So let's just think about what we can do. We can take the limit of each piece, and we will get to the limit we want for the whole thing. So ignore the 3 for now. Let's go to that second one, the 1 over x. That was one of them we said we needed to know, right? We got the limit as x approaches infinity of 1 over x. What did we say that was going to be? That's 0. Yeah, that's 0, right? So this thing's going to turn into a 0. And then we said that's not only true of something over x, it's true of something over x to any rational positive power. So this thing's going to turn into 0. In the bottom, ignore the 5 for right now. The limit as x approaches infinity of 4 over x, that's just like we had on the top, that turns into 0. And then we got 1 over x squared, that limit's going to be 0. So what are we left with? The limit as x approaches infinity of 3. What's that going to be? 3 is a constant, so the limit as x approaches anything of it is going to be 3. In the bottom, the limit as x approaches infinity of 5. Again, that's a constant, so its limit's just going to be 5. So we're saying the limit of this rational function as x gets really big, x approaches infinity, is 3/5. So that's an indication that since it's not infinity, right, it's some number, that's an indication that as we go to the right side of our graph, we have a horizontal asymptote. We have a horizontal asymptote at 3/5. So let's take a look. We look at the graph. So 3/5, that's 0.6. So as we go to the right on our graph, you can kind of tell that's getting kind of bounded by that y equals 0.6 line. So we'll have a horizontal asymptote there. So, word of caution. Think about this. Okay, let's ask ourselves this question. If we have a horizontal asymptote as we go to the right at some number, does that guarantee us that we have that same horizontal asymptote going to the left? It would be nice, but no. We could have a graph that, what if we have something that, and we have a horizontal asymptote going to the right, but we don't have that same asymptote going to the left. We could have another piece of our graph like down here somewhere and have another horizontal asymptote. So it's possible that we have different horizontal asymptotes to the right or to the left, or that even we only have one in one direction and not the other. So our choices, well, let me ask one other thing. Can we have more than 2 horizontal asymptotes? That one's tricky. That's a tricky question. Could we have more than 2 horizontal asymptotes? So let me like sketch in what that would look like. Maybe we've got a piece of the graph here in between these horizontal asymptotes, and I've got like some other piece. Yeah. And so maybe I'm like approaching this number there. That doesn't work, again, because of our vertical line test. If you try to have more than 2 horizontal asymptotes, you're going to get stuck in a situation where it fails the vertical line test, so then it's not going to be a function. So our choices for how many horizontal asymptotes a function has: 0, right? It could have none. We know lots of functions like that. We'd have 1 horizontal asymptote, and that 1 horizontal asymptote could work for the left, for the right, or both directions. Or we could have 2 horizontal asymptotes, where we approach one from the left as we go to the left, one as we go to the right. So this looks like, maybe looking at our graph, maybe that's a horizontal asymptote as we go toward negative infinity as well. So how could we check that? It's almost the same process. We just have to think about the signs. a little bit. So let's set it up. We want to know the limit. Goodness. As x approaches negative infinity. Well, if I can round. Of that same function, 3x squared minus x minus 2 over 5x squared plus 4x plus 1. Here, you'll get, once you get used to it, you don't have to necessarily write down this second step here where we've got so many x squareds in the bottom. You can just know that you're dividing by whatever power of x, figure out what you get when you simplify. So on the top, we divide by x squared, that leaves us with 3. And minus. And if we divide by x squared again, yeah, just 1 over x. And then have 2 over x squared. Bottom, we're getting the same thing we got last time. Okay. So let's look at what we get. Nothing really changes on this one because we don't have any just x's in there. We have some x's in denominators, but what happens to all those terms? Yeah, so this one goes to 0. 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 Yeah, but even if they're negative, they're still, the limit's going to be 0. We've got that theorem. As we're going toward positive infinity or negative infinity, the limit of something over any rational power of x, positive rational power of x, is going to be 0. We're guaranteed that. So the limit of this whole thing again is it. So yeah, on this one, yeah, we got one horizontal asymptote. It works both directions. Not always. Here, okay. So pick back up here. Let's look at this one. This one throws us a little bit of a curve. What jumps out is different on this one, anything? We don't just have a polynomial over a polynomial on the top. What's different? Got the square root. So thing we deal with here is how we represent the square root of x squared. Square root of x squared. So let me write it down. We want the limit as x approaches infinity of, let me get caught up with here. Square root of 2x squared plus 1 over 3x minus 5. Okay, so our rule, if we're just going by our rule is we divide everything by the largest power of x we have in the denominator, which is x. But we need to rewrite that to make it work underneath the radical. So be careful. Okay. Depending on how good of an algebra teacher you had, you may or may not have thought about this. So square root of x squared, what is that? Almost. Say that no, you were on the right there. Almost. So real quick. Yeah, you're right. Yep, you're on the right track there. So think about this. If we have this, so that would be the square root of 1 is 1. These match. So square root of x is x in that case. But what's that one? Negative 1 squared will be 1. Square root of 1 is 1. So they don't match this time, right? We got negative 1 over here, positive 1 over here. So square root of x would not be x there, it would be negative x. So the way we write it is absolute value. Sometimes we leave that little technicality out. And your teacher didn't lie to you. What they did is when you're like simplifying radicals and stuff with variables, they would say, assume variables represent positive numbers. You didn't have to worry about absolute value sometimes. Some teachers go ahead and make you worry about absolute value, and then seen it before. So here, we just have to be aware of that. But on this particular problem, are the x's we're dealing with, are they going to be positive or negative? Positive, because we're going toward positive infinity. So in this case, absolute value of x is just going to be x. So we're okay. So then when we do our division, so I'm going to do the bottom first because it's just like the last one. When we want to divide every term in the top, we can do this. Okay, when we move it inside the radical, we'll turn it into x squared. So we're trying to divide by x, but we want to do it under a radical, so that's the same thing as x squared in this case. So then when we simplify, okay, so inside the radical on the top, 2, 1 over x squared. Bottom, I got 3 minus 5 over x. So as we do each piece, remember, radical functions are, root functions are continuous, so we can think about moving the limit inside of the radical. So then we would just have the limit of 2 plus the limit of 1 over x squared. So the limit as we approach infinity of 1 over x squared, that is 0. And on the bottom we'll have the limit of 3 minus the limit as we get 0 on that one. So the limit of square root of 2 is just square root of 2. The limit of 3 is just 3. So square root of 2 over 3. As we go to the right, on this one, let's do toward negative infinity. Just a little bit different on this one. So keeping in mind this time our x values we're using, are they going to be positive or negative? They're going to be negative. So that's where we have a little bit more of a problem, okay, because we're going to have, like this situation where we have negative x, so that means we got to throw a minus sign out in front because we're going toward negative infinity. So we can do the same thing here, and we won't write down every detail on this one. But we're dividing by x squared. Just the thing we have to remember is that when we go under the radical, we've got negative. So it'll leave us with 2 plus 1 over x squared. And it's supposed to be squared on the bottom. Or no, it's not. Okay. So that minus sign just comes from the fact that we're going toward negative infinity. Right? We picked that minus sign up, that relationship. It doesn't bother us on the bottom. Here, this is, this limit 0, this limit 0. What's our limit on this one? Negative root 2. This time we've got 2 different horizontal asymptotes. As we move to really large x values on the right side, our horizontal asymptotes at root 2 over 3. As we go to the left side, we've got a horizontal asymptote at negative root 2 over 3. So those horizontal asymptotes there. And then on this problem, this is our last one. We'll do this one at the top. On this example, it asks us not only to find horizontal asymptotes, it asks us actually to go back and just find all the asymptotes. So here's our function. We got 2 horizontal asymptotes. That's the max we can have. Do you see anywhere? Not worrying about the limit now. I'm just looking at the function. Do you see anywhere it looks like we may have a vertical asymptote? When could have a vertical asymptote if what part's 0? The denominator. So if we want to know what x value that happens at, set it equal to 0. It was plus or minus. Is minus. Yeah, so what we're going to get 5 over 3. So we need to look around. Is that right? That's something else? Okay, I got you. All right. So we need to look around 5/3 and see what happens. Okay. You can just use test values here. Use test values here. So if you, sorry, wrong thing. If you come in from caught up here. If you come in from the right side, okay, so values bigger than 5/3 as you get closer and closer. And we're going to be getting big positive numbers. Right, we'll be getting positive values there, and then our the numerator is always going to be positive, right, because it's squared, so it's always positive. And then the denominator, when we're coming in at 5/3 from the right, our bottom's always going to be positive. So since we have positive values, you know we got a vertical asymptote going up toward infinity. If we come in from the other direction, the top's always positive, but when we come in from numbers smaller than 5/3, we're going to be getting negative answers. So we know it's got to be going down there, or negative infinity. So here's our graph. So our graph has a horizontal asymptote at root 2 over 3 going to the right, horizontal asymptote at negative root 2 over 3 going to the left, and then we have a vertical asymptote at 5/3, and we know we approach infinity coming from the right, negative infinity coming from the far right. Good stopping place. You glad? Glad to be done for today. We'll stop there. Like I said, you don't even have to